In this lecture, we will introduce a very important secondary battery, which is the lead acid battery. We cannot do justice to this topic because I feel an entire course can be taught just using lead acid battery. Um, it has a lot of fundamental science, practical application, and so on. So, just to give you an idea of the scope of lead acid battery, you should take a look at the Wikipedia link. Okay, so why is this technology so important? First, it was came into practice in 1860. Okay, so it's a very old technology. Just the implementation of this technology um, gives you some ideas on how technology comes into fruition. Okay, so this was implemented for the first time by Plante, who was basically an inventor. In those times, uh, there was nothing called fundamentals of electrochemistry and so on. So they were all inventors who studied the work of previous inventors and scientists, and then put things together. Okay, so if you look at history of technology, many things were assembled in that manner. So now in hindsight, we can understand, rationalize why things work the way they work. But it's also important to understand how technologies come into fruition. So a secondary battery is um, something wherein chemical energy is converted to electrical energy, right? So all you need is an exothermic reaction. So during discharge, this is an exothermic reaction. So these reactants go on to form these products. So why is it a secondary battery? Because this can be recharged. Okay, so that is an endothermic process. So you supply electrical energy and reverse these chemicals into these chemicals. Okay, so if this can be done for a large number of cycles, then you have a good secondary battery. Okay, so many of these things we have dealt with in previous lectures, but we can still try to discuss them in the context of lead acid battery. So the lead acid battery voltage can be obtained from the delta G of this reaction. Um, and then with that, you can calculate the standard voltage. So it has two electrodes, positive electrode and negative electrode, which indicates the direction of conventional current. In this case, is lead and lead dioxide. So note here, lead is in +4 state, and here lead is in 0th state. Okay, so I'm referring to the oxidation number. So what is important to notice is the lead sulfate that is formed, in which lead is in +2 state, is in the form of a solid. Okay, so this is where this, when you form lead sulfate from lead, that is deposited here, and when lead sulfate is from lead dioxide, it is again deposited close to the electrode or on the electrode itself. This is a very important point. We'll come back to this in a bit. Okay, so if you take the standard, or if you take the delta G of the reaction, you can get this number, which is the voltage that is being referred to here. So this voltage typically is used for doing electrical work, right? So electrical work we have defined in previous lecture. When a charge is transferred across an electrochemical potential, we can obtain a formula for electrical work. So this basically conversion of exothermic chemical reaction to electrical work. That's what we see in this battery and any other battery. Let's get into slightly more thermodynamics. So we have this overall reaction. Um, because we are looking at the potential using free energies, it's good to write the free energy in terms of delta G is equal to delta G naught RT ln equilibrium constant, right? So this is from basic chemical thermodynamics. We have looked at these things in previous lectures. If you're unsure of this expression, please look at the previous lectures. These would be under electrochemical thermodynamics, series of lectures that were given under electrochemical thermodynamics. So this number is minus 387. So this number is minus 375. That corresponds to delta G naught. These two are one and the same. And this is expressed here. Okay, so you express um, activity in terms of activity coefficients and concentration. Again, these were covered in electrochemical thermodynamics. We went on to do Debye-Huckel theory and so on. So please refer to those lectures. So if you put in the average concentration during the operation of the lead acid battery, that amounts to 3000 millimolar. So if you put this number along with this number, you get this number. Okay, so which in turn gives rise to this potential. So why is lead acid battery rechargeable? Why is it a secondary battery? So this is an intricate feature of nature which has made this possible. Okay, so if supposing the lead sulfate that was formed was entirely soluble in the electrolyte, this lead sulfate would have been dispersed in the electrolyte. Okay, so that would uh, not be ideal. So because lead sulfate is very minimally soluble in the electrolyte, the lead sulfate that is formed on either of the electrode gets deposited close to the electrode or on top of the electrode. So therefore, when you do the recharging process, when you charge the battery again, this lead sulfate, which was just close to the electrode, gets converted to lead in this side. And this lead sulfate, which was close to the electrode or on top of this electrode, uh, gets converted to lead dioxide. So this feature, that is lead sulfate not being soluble in the electrolyte, is a very, very important feature that makes lead acid battery rechargeable. So that's why you may have thousands and thousands of possible battery chemistry. Okay, so all these things don't become technology because there are only few things that satisfy the many features. Okay, so in this case, one of the feature is we should have a system that is rechargeable. Okay, so for that, that lead sulfate is minimally soluble in the electrolyte is an important feature. And then lead at that time was widely available. So this lead acid battery became a very extensive technology. In the previous lecture, I also mentioned how Edison used this for the first electric vehicles in late 1880s. Okay, so this was Plante implemented this battery chemistry in 1860. In 20 years or so, Edison tried to get this out as a or early 1900s. Okay, he brought it out as an electric vehicle. It didn't take off for a variety of reasons. Hopefully, electric vehicles will become a reality. Widely practiced electric vehicle will become a reality in the next few years. So let's move on. So the discharging voltage is less than this voltage mentioned here. During the discharging process, the reaction occurs in predominantly in one direction. Okay, so here we had shown the equilibrium between these two reactants and products, but during the discharging process, this set of reactants get converted to this set of products, and this set of reactants get converted to this set of products. In both these cases, lead sulfate gets formed just on top of the electrode, by the side of the electrode. So this voltage is less than this voltage, okay? This was the voltage at equilibrium, let's say, and this is the voltage during the discharging process. So during the charge process, if you compare this against this, the direction of the reactions become is in the opposite direction. So if this is the reaction in the discharging process, during the charging process, that gets reversed. Okay, so these two you should notice and compare and with this set of reaction. So this gets reversed. So lead sulfate gets converted to lead dioxide at on one electrode. Lead sulfate gets converted to lead in the other electrode. So what was an anode will become a cathode, and the other way around. Okay, so so anodes and cathodes are defined in terms of oxidation and reduction, but because in one cycle, uh, in a secondary battery, the reactions gets reversed in charging and discharging. So what was an anode will be referred to as a cathode in when you're charging and discharging. I mean, so this gets cyclically switched. And again, just to emphasize the positive, when you talk about a positive electrode, we are talking about just the direction of conventional current. So during charging process, you have to apply more than 2.1. So here you are applying 2.2, and you are reversing the process. Again, we can discuss the lead acid battery chemistry under three possible modes. So when you say the lead acid battery is in a galvanic mode, what we are referring to is the battery is getting discharged. Okay, so it is acting like a power source. When the battery is under an electrolytic mode, what we are referring to is that we are supplying a supplying external electrical energy and driving an endothermic reaction. So in the galvanic mode, the the reaction is there is an exothermic change in the chemical reaction-free energy. So there is a spontaneous conversion of chemical energy to electrical energy. Okay, but in this mode, you have to drive the reaction via an external power source. So this is also discussed in what is called a polarization curve. So you have a null voltage, which in this case is 2.01 or so. You can drive the reaction using external electrical energy. When you apply more than 2.01, you still have electrolytic current. So in when you below 2.01, there is galvanic current. That is, the battery operates to convert. Battery operates in such a way the chemical energy is converted to electrical energy. So this is to be understood, and try to correlate this with the charging and discharging reaction, and also the expressions for delta G, which we discussed in the previous slides. So some more features. So as I said, that the voltage can always be correlated to delta G. And what we are changing in the charging process and discharging process is basically these terms. So during the operation of the battery, that is during the discharge of the battery, we said the average concentration was in this was the average concentration of these terms. However, in a fully charged battery, uh, this concentration is increased to 5.2 molar. Okay, so because of that, you can change this number and then get altogether a different value for the potential of a battery. So the main control you have during the charging process is to change this quantity, and during the discharging process, this changes spontaneously. So you don't really have a control. I mean, in the sense that you can still control the rate of change of rate of discharging, that is by controlling the amount of current, discharge current. But if you want to change these numbers and correspondingly change the battery voltage, that you do during the charging process. So what is to be noted is these numbers during the discharge process gets converted to 5.2 molar. Okay, so this is the concentration I'm referring to. This concentration gets converted to 5.2 molar via charging. So if you change this number, um, you can correlate that to voltages mentioned in this side of the polarization curve. These are the voltage that occur during the discharging process. So beyond this, it's the charging process. Beyond on this side, it is the discharging process, and the current gets to be referred in different terminologies. Here you refer to electrolytic current when you do undertake an endothermic process. This is an exothermic process, and you refer to this current as a galvanic current. So lead acid battery has some disadvantages too. First, lead is not a um, it's not a sustainable process. Okay, so this has a lot of environmental penalty. So this has to be recycled. It should not be just thrown out. Okay, so this is a very important feature. Okay, so the sustainability of materials is very, very critical, and lead is not considered to be a very sustainable material. So besides that, there are some extraneous reactions. One reaction is an extraneous corrosion reaction. So this is the reaction you want. That is, you want lead to be converted to lead sulfate. However, the unwanted reaction is the corrosion reaction. Lead can just convert it to lead dioxide. Okay, so you don't want that, and this doesn't really contribute to your cell potential. So this is something that has to be avoided. So there are many ways of addressing this corrosion issue. We won't go into this. All these things have to do with the practice of lead acid battery. So we don't have the time to go into this, but these are all very, very important topics uh, that are probably first implemented in the industry. I mean, the how to suppress solution was first implemented by large scale experimentation in the industry, and the science of corrosion suppression was understood later. Okay, so in most of the cases of development of technology, um, the some solution, perhaps in an ad hoc manner, is introduced in the industry, and why that solution works is understood later by some fundamental research done in the industry, okay, in the university. So corrosion is one such extraneous reaction which has to be suppressed. There are other in the extraneous reaction when I unwanted reactions, and one of the main extraneous reaction are gas evolution reaction. Note the potential of operation is more than 1.23. Why is 1.23 important? 1.23 is the minimal energy or minimum potential that you need to supply to water to split water. Okay, that is, if you do electrolysis of water, typically electrolysis becomes dominant when you supply, let's say, about 1.6. Okay, so because of certain over potential in the electrodes, um, the when you supply 1.23, nothing happens. So at around 1.6, typically, if you have a good electrocatalyst, anode and cathode electrocatalyst, oxygen and hydrogen will get evolved in water electrolysis. So if you look at a lead acid battery, this is an aqueous battery. You have water in this system, but your voltage is around 2. Okay, so you may ask the question, why is that you don't see mostly hydrogen evolution and oxygen evolution? Again, this is because of a certain quirk of nature. Okay, one quirk of nature which made lead acid battery rechargeable is that lead sulfate is not soluble in the electrolyte. Another um, useful quirk of nature is that these two electrodes are very bad at oxygen evolution and hydrogen evolution. I mean, in the sense that if you use these as electrocatalysts for hydrogen and oxygen evolution, these are poor electrocatalysts. So this makes it possible to suppress this two gas evolution reaction. So in a lead acid battery, these two are disadvantages. So because these two electrodes are poor in electrocatalyzing these two reactions, so that is a good feature of these two electrodes. So however, even though they are bad electrocatalysts, some amount of oxygen evolution and hydrogen evolution do occur. So, um, so if you have an UPS system with lead acid battery, especially in the old lead acid batteries, you have to top up. Okay, there is this term called topping up. So because water gets consumed in this manner, so you have to add some water periodically. Okay, so 20, 30 years ago, this was more common. Okay, the lead acid batteries had this problem a lot. So typically, the lead acid batteries were not used in UPS in those times. They were used in cars. Okay, during starting the car, you use the lead acid battery. Um, in often we have to refill the lead acid battery with some water. Okay, so typically one way to look at uh, when topping up is needed is to look at the density of the electrolyte. Density of the electrolyte is a measure of how much water is in the electrolyte. So when the density changes beyond a particular point, you go and top up, add some water into the lead acid battery. So these have been addressed. We won't go into this now. Nowadays, lead acid battery require very less maintenance. So we refer to such a battery as maintenance-free battery. Okay, so we won't go into this because yeah, that gets into a lot of practice of lead acid battery, but we can address such questions in the class. What is next? We would look into some other secondary battery chemistries. So some were not successful, even though they had some initial promise, but still some other battery chemistries are also practiced, NiCad, nickel hydrogen, and so on. So we will look at these battery chemistries in the next lecture. Thank you.